Hello and welcome to lecture 26 of Math 1B03. As you can probably tell, I'm not in my usual spot. I'm in my office again today. I'm using a different computer so that the camera is actually not as good as the other ones. So I'm actually going to make that disappear right now, just so that you don't have to see almost a black and white version of me. So what we're going to be doing today is look at section 4.5 on dimensions of vector spaces. Okay, so today's topic, as obviously from the title, is about dimension, but the way that you can think about it is what we're going to be looking at is looking at a way of measuring the size of a vector space. Okay, so we're going to go back, and here I have three sets of vectors, 1, 0, 0, 1, and then I have the set 1, 0, and 3 minus 5, and then I have the set 1, 0, and 0 minus 5. Now, these vectors actually come from yesterday's lecture, or lecture 25, and all of these sets of vectors have the same property in that they're all bases for R2. So bases are not unique, and hopefully you've seen that from what we've talked about so far. So bases are not unique, but there is something that is similar between all these three sets, right? Even though that they're different, they all have the same number of elements. And so you should be asking yourself, is that a coincidence? And the answer is no. Okay, and because this is not a coincidence, there's actually something deeper going on here. And that's what the next theorem states. We'll just state the theorem right off the bat, which says that if you have a vector space with a basis with n elements, so you find a basis for your vector space and you count the number of elements, then it has the property that every basis of V has n elements. So what this means is if you have a vector space and you find a basis and somebody else in the class finds a basis for the same vector space, even though they may not be the same basis collection of vectors, you will both end up with the same number of elements. And so because there's a unique number showing up attached to it, we want to give a name to that. So let's talk about this. So if B has a basis B, then we're going to say that our vector space is finite dimensional if the number of things in our basis is less than infinity. So we have a finite number of elements in our basis. So it's a finite dimensional vector space. And we say that the dimension of the vector space is simply the number of things in this basis. So this definition makes sense because the last theorem says it doesn't matter which basis you pick, you'll always find the same number. So the dimension is always just going to be the number of elements in any specific basis for the vector space. A couple things to pay attention to is if your vector space is the zero space, then the dimension of your vector space is said to be 0. And if V does not have a finite basis, then we say that V is infinite dimensional. Now we don't see a lot of infinite dimensional vector spaces in Math 1B03, but they pop up with some regularity in some of your upper year courses. And I will give you an example in a second. So let's kind of just stop for a second and think about, things that we've looked at before and how we can use that information to compute their dimension. Right? So when you think of Rn, a basis you should be thinking of course, is the standard basis. So E1 up to En, right? So this is the standard basis. And then the theorem says, well, once you find one basis, you can compute its dimension. And so the dimension of Rn is equal to n. And of course, this should make sense. Rn is usually the way that we think of it is how many degrees of freedom. And so that's what the dimension is measuring here. What about a basis for Pn? Well, the standard basis for Pn is 1 t squared up to Tn plus 1. So we found one basis, and now to compute the dimension, we just count the number of things in here. And here, pay attention that it's not, oh, sorry, that's not that's just an n. There's not n things in here, there are n plus 1 things here, because you want to think of this as t to the 1, t squared. So you can think of this guy at the beginning as t to the 0. So there's n plus 1 elements. We talked about a basis for M22, which is all the 2 by 2 matrices. And a basis for this is 1, 0, 0, 0, or a matrix with all zeros except 1 in one of the spots as we move around the matrix. So this is a basis for M22, and this implies that the dimension of M2 times 2 is equal to 4, because I have four matrices in my set. And you can think about this for a second, but then it's clear that the dimension of all the m by n matrices is going to be m times n. Okay, and let me finish this part of today's, oops, undo that. Let's finish this little part of today's lecture. It's just giving you an infinite dimensional vector space. So we let P infinity be the set of all polynomials of any degree. Okay, and you can check that this is a space spanned by 1, t, t squared, t cubed, and so on. And you need all of these polynomials in order to describe all the polynomials of any degree. So this implies that the dimension of P infinity is infinity. And that's because since the basis has an infinite number of elements. So we're going to take a quick pause here, and in the next part we'll talk about some of the properties of dimension.